We're going to do the chain rule for multivariable functions. But before that, let's look back on the chain rule for single variable calculus. So here's a function and a function, and I'm going to differentiate it, chain rule. We know that the way I would write it, take the derivative of the outside, leave the middle alone, multiplied by the derivative of what's inside. But let's use the different notation, the D notation for that. This derivative of f with respect to g, leave g alone, that means we're taking df dg. And this g prime, that's over here, that's dg dx, and it kind of looks like these dg's cancel out and I get df dx, which is what I want when I'm taking the derivative. So now multivariable chain rule. So I've got a function now, z is a function of x and y, and x and y are functions of a parameter, let's say t. So I want dx dt. Now we got to watch our d's here, right? This dx dt means ultimately t is like the ultimate independent variable. You pick a t that gives you an x and a y. Once the x and the y are locked down, because you picked a t, you plug it in here and you get a z. So z is a dependent variable, t is the ultimate independent variable. What are x and y? Z depends on x and y, but x and y depend on t. We're going to call those later intermediate variables. So by the time we're done this chain rule, learning this multivariable chain rule, we're going to have not just independent variables and dependent variables, but we're going to have intermediate variables as well, things in the middle. All right, so I want to find how z is changing with respect to time. Our chain rule says we're going to have df dx, but then dx dt, but notice it's like these dt's cancel out and that's f of t. Likewise, these dy's cancel out and that's like df dt, and we're adding them together. Why does this make even any sense at all? Well, as we change t, x changes. As we change x, z changes. As we change t, y changes. As we change y, z changes. So we have to take into account when we change t, how z changes with both the x changing and the y changing. So it makes sense that we have those pieces. Now, and it makes sense that our dx's cancel out, but I am canceling these, and our dy's cancel out to give us an f of t and an f of t. Not the same, they're like two different pieces that add together to give the total change. So this is our change that happens when we change t and it changes x and changes z. And this is our change that happens when we change t and it changes y and that changes z. All right, but let's look at our d's here, because I got funny d's for these partial derivatives. So this is a partial derivative because f is a function of more than one variable, and I'm only differentiating with respect to one of them, x. Likewise, this is a partial derivative. Whereas my dx dt, x is a function of t, but it's only a function of t, so it's a single variable function. So I'm using regular d's. Also over here, now this is a bit, z is a function of two variables, but ultimately it's a function of only one variable, the variable I'm changing, so I'm using regular d's here. Let's see this in an example. So I want to find z prime. Oh yeah, that's unambiguous because z depends on x and y, x depends on t, and y depends on t. So when I write z prime, it's unambiguous because I'm saying what's the derivative of z with respect to the ultimate independent variable, t. So I need these pieces then. So let's get our df dx. So that means I'm differentiating this z function. I guess you could even say, we could make that dz dx as well. I'm differentiating my function here with respect to x, treating everything as a constant, y as a constant. So that's going to be y cubed minus 3. So there's my derivative with respect to x, and now I'm multiplying it by the derivative of x with respect to t, and that's just 3. Plus, now I need my derivative of the function, the z function, with respect to y. So that's going to be 3xy, so x is a constant in this derivative, squared minus 0. And multiply that by the derivative of the y function with respect to t. So 3t squared. Done. There's my answer using this formula. Let's sort of sit back for a second though, because I know you're thinking, all right, I have the derivative, but it's got y's and x's and t's in it. The t's are the ultimate independent variable. The x's and y's, we're going to call those later intermediate variables. My formula has all of these pieces in it. How do I actually get a number? Well, how would you actually get a number? If you tell me what the t is, so if I want the derivative, let's continue this example and say we want this, but evaluated at t equal 1. So I'm going to get a number. I want the slope when t is equal to 1. So when t is equal to 1, I know what this is, but what's x and y? Well, I could use the formulas to figure that out, right? When t is equal to 1, let's put that in there. When t is equal to 1, x is equal to 10. And y is equal to 1. Now I have values to plug in here. So this is going to be 1,000 minus 3. So that's going to be 997 times 3 plus, okay, 100, no, y is equal to 1. Duh. So this is going to be minus 2. Minus 2 times 3 plus 30 times, when t is equal to 1, 3. So 90 minus 6, 84. So we get a value, but we have to get the values of the intermediate variable as we go. So this isn't too bad following this formula. But I remember when I first learned this when I was taking multivariable calculus, I remember getting to this section, and like they said, do this question, and the first thing I did, do this homework question. The first thing I did was go to the back of the book, look at the homework question, then figure out how to do it. I know my professor wanted me to read through the chapter and then do the homework, but I was like every other student. I did the thing backwards. I read the questions first and then went and figured out how to do them. So what I came up with was, or what I thought was, this seems like a lot of work, right? Reading this whole section. If I have the Z formula, why can't I, everywhere there's an X, just substitute it in? Substitute what X is in terms of T. So everywhere there's an X, just put the 3T minus 7. Everywhere there's a Y, just put the T cubed. Essentially, I'll just get rid of the intermediate variables. Now z is directly a function of time, and I know how to take the derivative of this. Let's do that then. That would be z prime is equal to, now I got to do product rule here. So I do derivative of the first, leave the second alone, plus leave the first alone, times the derivative of the second. All right, I got to do chain rule here. That's going to be 3, leave the middle alone, so that's t cubed. Subtract 1 from the exponent. Finally, now chain rule times the derivative of what's inside, so there's my 3t squared. So all of this is just the derivative of this first piece. Okay, so now minus 3 times the derivative of, oh, well, that's just 3. And here's my answer. And you know, young me would have argued, oh, this is even better, because if the question was, what's the slope when t is equal to 1, I don't have to figure out the x's and the y's. I can just plug 1 all the way in here and get the value. I've gotten rid of those x and y's. Didn't need them. Now, old me, the one making the video, would say, well, yeah, this is the right answer, and it did look easier, but you've destroyed some of the actual flavor of the math. There was a reason why the question was set up like this, where z is a function of x and y, and x is a separate function of time, and y is a separate function of time. And by you getting rid of the intermediate variables, the x and the y, you've destroyed that piece of information. And then young me might have said, well, yeah, whatever, I get the right answer. But let's listen to old me, because old me's making the video. What could this represent? Well, this could be a mountain, and given, you know, the height of the mountain given by your x, y coordinates on a map, longitude and latitude or something like that, and your longitude and latitude is given by a function of time, so you're moving around some road as a function of time, and the z is saying how you're going up and down. By eliminating the x and the y, now I've just got altitude as a function of time, and if I were to graph this altitude as a function of time, all you see is time along the axis and altitude. You see me going up and down as time goes on. You don't know if I'm in an elevator or jumping up and down or what. I've eliminated that flavor of me being on the map, or the x being longitude and the y being latitude. You've lost that piece of information, and it's difficult to undo it. Anyway, it's good for us to know both ways, but we can always fall back on the cheap way that I would have done as a student to sort of check my answer. And let's look a little bit deeper at this cheap way, because I said they're the same. Can we even see that they're the same? Well, there's this 3, and we said this piece, and I'm going to group that together. This piece is supposed to be like this piece. Well, do I see that? Well, y is t cubed. So that's y, and that's y. X is 3t plus 7. So that's x. So I see 3y cubed here, 3y cubed. Minus 3, I see that piece here. And 3x, y squared, 3t, I see this piece here. So the pieces are there, but it's more difficult to kind of go backwards to get them back out. Like, how do I know not to substitute an x and a y in for here? Well, you don't. We just saw this sort of nice 3t plus 7 was a chunk of algebra that I could see and replace with x. Anyway, this video is on the chain rule. We're supposed to be using the chain rule. And when functions get more and more complicated, it's easier to know the chain rule rather than try and circumvent it by getting rid of the intermediate variables. So now let's expand upon that chain rule idea. Z is still a function of x and y. It's still a multivariable function, but the x and the y are also multivariable functions. So z depends on x and y, x depends on s and t, and y depends on s and t. So now there's two independent variables, s and t. There's two intermediate variables, the x and the y, and there's one dependent variable, the z. Our formula for dz dt looks pretty much the same, except for, since everything's a multivariable function, all of the d's are the funny d's. So the difference between this formula and our original formula is this one has some regular d's, because if I'm differentiating a single variable function, I'm just using the regular d's. So there's no z prime or anything here. I can't say z prime because I don't know if that means the derivative with respect to s or the derivative with respect to t. There's some ambiguity there. But the setup of the function works the same. So let's learn this by example then. Let's do this by example. And again, I'm asking for z sub s here. And you totally could do this the sort of cheap way, right? Everywhere there's an x in my formula, I could put a 3t plus 7s. Everywhere there's a y in my formula, I could put an s squared t cubed, and then that would make z directly a function of s and t, and then I could just plain differentiate it. You could do that, but I lose some of the flavor. And I have to do all that algebra to start. So let's do what we do here. I want to take the derivative with respect to s. So I need function with respect to x times x with respect to s. Function with respect to x times x with respect to s in this case, right? The rule I wrote out with t, but we're differentiating with respect to s. So now let's differentiate this function with respect to x. That's going to be y cubed minus 3. And now x with respect to s is 7. Plus, I need the function with respect to y now. So 3x y squared minus 0 multiply by the derivative of y with respect to s. So that's going to be 2s t cubed. Done. So actually that's not too bad, right? I think that's easier. And we don't have to build that z of s and t function, which requires a ton of algebra. And if you said, well, I want the derivative as a function strictly of s and t, now I can replace all the y's with s squared t cubes if I want to. I can get that. But there's me taking the derivative. That's the slope formula. All right. So now we have intermediate variables, and it says there make a tree diagram. The tree diagram to which I am referring, let's draw that. The tree diagram to me is a good way to organize these things. It's a good way to remember. Here I've got the z, the dependent variable, and it's a function of x and it's a function of y. X is a function of s, and x is a function of t. Y is a function of s, and y is a function of t. Now we want dz ds. So I want this piece and this piece, and we're adding them together. I'm going to add this answer together. So z and x, that's z with respect to x, and this is x with respect to s, x with respect to s. This is z with respect to y, and this is y with respect to s. And now I want s, so I'm using these branches with the s's here. So it's this times this, plus, so that's underlined, that's supposed to be underlined, plus this times this. And that's using the tree diagram to sort of, instead of memorizing, or I guess we're not memorizing, you're just understanding these formula, but the tree diagram keeps me organized so I don't miss anything. That's what I mean by make the tree diagram. Would the tree diagram have worked up here? Yeah. So up here, the tree diagram would be z is a function of x and y, and x is a function of t, and y is a function of t. This is z sub x, and this is z sub y. This is x sub t, but that looks a little funny because it's only, in our first example, x was only a function of time. So I'm going to write like x prime, y is a function of time, that's y prime. And so there's only two branches, but I want to add them together because I want everything with t's here. So dx dt is equal to z sub x, x prime, plus z sub y, y prime. Now there's this formula. I'm mixing my notations, but I don't have any of the funny d's, so that's a good thing. But the tree diagram works in this case. All right, let's do another example. And this one, this one I want the second derivative and the first derivative. Let's do our first derivative with let's draw a tree diagram for that one also, to sort of organize my thoughts as what I want. So let's check out what's happening first before we draw. Z is a function of x and y. X is a function of s and t. Y is a function of s and t. I want z sub s here. It's not the exact same example that we had before, but it's pretty close. So, tree diagram. Okay. Z is a function of x and y. X is a function of t and s. Y is a function of t and s. I want the derivative with respect to s, so I want this piece and this piece. This is z sub x. This is z sub y, partial derivatives. These will also be partial derivatives. That's x sub s and y sub s. So I want z sub x times what I want. I want z sub s is going to be z sub x times x sub s plus this other branch, z sub y times y sub s. All right, let's do this. So I want z sub x, so that would be y cubed minus 6x times x sub s. So the derivative of x with respect to s is just 7. Plus, now I need z sub y, so the derivative with respect to y. Keeps putting my subscript way up there. Minus 0 multiplied by the derivative of y with respect to s. Okay, done. We at least did this first piece, and that's pretty much just another example of the things that we had seen before. But now I need to differentiate it again with respect to s. But now my function has, that I'm going to differentiate, it's got x's and y's and s's and t's in it. So now it's going to be a little bit more involved. But some of this is not too bad, right? Because if I'm going to differentiate this piece again, so, I mean, that's just going to throw another s there. And all I have to do is differentiate this piece with respect to s, and then differentiate this piece with respect to s. Differentiating this with respect to s, that's just I'm just going to use my tree diagram. Let's do that. We're going to use the method we had, because this is just a 7. Let's put this, I was going to say let's multiply this 7 through. I'm not going to do that. I'm just going to leave it as the constant that it is. So 7 times, and now I'm differentiating this piece with respect to s. So I have to do the chain rule again. So it's differentiate this with respect to x times the derivative of x with respect to s, which is the same as it was last time, plus the derivative of this piece with respect to y times the derivative of y with respect to s, which is the same as it was before. So this is the derivative of this with respect to s. Plus, now I got to differentiate this. All right. The product of two things. So I still have to differentiate this. The product of two things. So I'm going to use product rule. So it's going to be derivative of the first, leave the second alone, plus leave the first alone times the derivative of the second. So those primes right now, to me, mean differentiate. I don't like that notation, because it's going to be partial derivatives. So let's, instead of making them primes, let's do, I got to differentiate that with respect to s. Leave this alone. I got to differentiate the second bracket with respect to s. That's easy. That's more accurate. So now let's complete these pieces. So this is product rule on this piece here. Oh, okay, now let's actually differentiating this with respect to s. It's only a function of s and t, so this is easy, right? T is a constant, 2 is a constant, so there, that's that derivative. Done. So now this piece is finished. It's just here. I need to differentiate that with respect to s. That's going to be chain rule again. So it's a function of x and y. So this, I'm going to put a square bracket around it so that we can work inside here. So I'm going to do the derivative of this with respect to x, which is just 3y squared, times the derivative of x with respect to s, plus the derivative of this function with respect to y, times the derivative of y with respect to s. And we're set. There it is. Messy? Yeah. And if I was not confident with my answer, I could sub in the x and sub in the y, make z a function of strictly s and t, and then just take the second derivative. You could do it that way. But I think you'll find that the chain rule, the multivariable chain rule, is a little bit easier because you don't have to do all that substitution. Let's do one more example. So here's our example, our last example. And I've tried to make this one so that we got variables all over the place. So f is a function of x and y and z, and x is a function, x, y, and z are both functions of s and t. So it's like multivariable. The tree diagram is going to keep me organized. So let's draw our tree diagram. And I want f sub s. So f is a function of x and y and z. Z. Anyway, there it is, x, y, z. Now, x is a function of s and t, y is a function of s and t, and z is a function of s and t. Now, I know you're saying, well, wait a minute. Y is only a function of t, not of s. Yeah, that's okay. The tree diagram is organizing my thoughts. So I'm going to keep it there and for a second marvel at the tree diagram and how that it doesn't matter how many variables are here, I can deal with it at different levels. And although it's not in this problem, if t were somehow a function of s, then I'd need a branch down here as well. We could even deal with situations like that. It's not an issue here, but we could handle it. Make another level down here. S is a function of s, s equals s, and the derivative of s equals s is 1. Anyway, let's see what we need. We want the derivative with respect to s. So I need this piece, and this piece added together. So I'm going to end up with f sub x for here times x sub s plus f sub y times y sub s plus f sub z times z sub s. And I'm going to add those all together. Now, let's clean this up right away if we have it here. Y sub s is 0. So this y sub s piece is 0. It's still there. It'll get rid of it. When I throw 0 in, this whole piece will disappear. That's fine. The tree can handle it. Let's see what our derivatives are. So I need our x sub s. That's going to be 2. I need our y sub s. I'll write it in here for completeness. We don't need it. We already did it. It's 0. There it is. And our z sub s is equal to 4s t to the 5th. Now I need my f sub x, f sub y, and f sub z. So f sub x, taking the derivative, partial derivative with respect to x, so that's going to be y squared cos x, that's a 0, plus z squared. I need f sub y, which is going to be 2y sine x plus z over y plus 0. There's no y's in here. And finally, f sub z, which is going to be 0 ln y plus 2xz. Okay, I have all the pieces. So now let's put all the pieces together using the formula that we made on our tree diagram. So f sub s is going to be equal to we need the x first. The derivative with respect to x, the x with respect to s. The derivative with respect to y, then y with respect to s. And yeah, it's a 0, but we'll put it in there for pedagogical purposes. Finally, the derivative with respect to z, and z with respect to s. Done. So I think the tree diagram in this multivariable chain rule is a lot easier than the way that I first started doing it when I was a student. This is a better idea, and it's a more versatile idea. Anyway, now it's just practice.